So let me just sketch out how this works. We look at a system of 3 disks on equilateral triangle with the same diameter. So they have a symmetry which has many names, but I'll call it dihedral group in 3 dimension, or you can call it cyclic group on 3 elements, C3, but with a flip, with reflections. In that case, the fundamental domain is just any 1/6 of configuration space. And the phase space that comes with it, the momentum coordinate is very easy. It's only 1-dimensional because it's only the angle of how you go out. So dynamics is in 3 dimensions. So this suffices in this case. If you look at some PD, it might look more complicated. So fundamental domain is circle, line, mirror, mirror. And you already learned how to think of things. So for example, there are 2, 3 cycles going one way or the other, but in fundamental domain there is only cycle 1. There are things moving like that. In fundamental domain there is only 1. This was 1, 2, 3. 3, 2, 1 going the other way. But in fundamental domain, this all gets very simple, so you know all that stuff. Here is what all this discussion so far about taking traces does. Eventually, when you derive a trace formula, the way you derive it is that for finite time, you have a finite number of unstable cycles, and you look at little tubes in phase space to traces. And for example, we know that this is a repeat of the same thing twice up to reflection. That's why we have only 1 fixed point, not 2. Here we have 3, but we know that they're equal segments. That's why we have only 1 fixed point. So in this case, the relative prime cycles are either half of the length of the cycle or 1/3 of the length of the cycle, because I can use this thing to take 1/3, and I can use reflections to take 1/2. Or they could be asymmetric, meaning that the cycle in the reduced space is the same length as in the original space. All 3 cases happen. Then trace to spectral determinant in zeta function formulation, which was easier than spectral functions. In the original case, we got something which was 1 minus the weight of the periodic orbit, which we call T with subscript P, which is a little trace computed on the orbit. But now every orbit is being weighted by these characters. So there's a trace of some operator, and when you exponentiate a trace, you'll get a determinant. So now you'll find the determinant of 1 minus the operation needed to bring this G can be written as a product of 3 terms. And the reason is that groups with 6 elements can always be brought to a form where there is irreducible space that corresponds to symmetric state, antisymmetric. People who have seen Young tableau, raise your hand. Life is tough. And then there is irreducible representation of dimension 2, which is called mixed symmetry. And that happens twice. So any group element that we wrote before can be written as a sum of these guys because they're not mixed. The irreducible representation H and there are 3 of them. And then we need characters. Here is a D3 character table. So, any group, any book on group theory, or any chemistry book on quantum mechanics will have this, because these guys are masters, they really need it. So D3 has 2 representations, antisymmetric, symmetric, antisymmetric, and mixed. And it has 3 kinds of elements, group elements. There is identity that has nothing. Then there are 2 operations which move you around. You can turn by 1/3 or 2/3. So if 1/3 is called capital C and 2/3 is doing it twice, that's a group of its own. And then it has 1 element which is reflection. And of course we can bring it, there are 3 reflections, but as a class there's only 1 type of thing. So you can either rotate or you can reflect. And then this trace of these elements, this one is always 1 for all of them. So it gives the equal weight to all the ways from which you got from your fundamental domain to the other copies of it. Then the antisymmetric one has a non-obvious property that this is -1. And the mixed symmetry is totally non-obvious. Computation, you can do it by hand. So this is an easier calculation, computing character table. So in the trace formula, these numbers show up. So either 1s or -1s or no contribution to the mixed symmetry, or for some reason identity contributes twice. That's because identity is 2-dimensional representation. That's how the terms in this expansion are computed. They use this character table, and you find in general that symmetric space, so this is contribution to fully symmetric functions, this is fully antisymmetric functions on your billiard space, and this is the mixed ones. You get a character of 1, which is just 1. I haven't taken care of relative primes yet. And this one can pick up a sign, so there is a character of A1. So this is either 1 or -1, depending on where this is a periodic orbit or relative periodic orbit. And then this 2-dimensional thing, when you express determinant in terms of traces, you get things that are quadratic. So this part I find totally non-obvious, and it happens twice. The antisymmetric representation sneaks in. An example. In the book, this is done for this symmetry, also for tiling, square tiling, which are the 2 typical problems that you need. If this group element here, if H is either rotation or by 1/3 or 2/3. So that's simplest example is this cycle here. Then on the left-hand side, what you get is 1 minus prime cycle repeated 3 times. So there's a cube here, and there are 2 of them. So you get a square here. According to this formula, it factorizes as 1 minus while in the original space you had 2 3 cycles, that's this square. Each cycle was 3 repeats of the prime cycle, so you really worked unnecessarily too hard in a big space. In a fundamental domain, symmetric space, you only get 1 contribution, 1 prime cycle, and you're done. You can expand both sides and you can see there's an equality. If I look at this guy here, so if H is one of the reflections, sigma I, then I'll find on the left-hand side 1 minus P tilde squared. But I have 3 of them, so to the Q power in my cycle.